Hello, everyone. Welcome to today's live broadcast, Extraction of PFAS from Mixed Matrices using a rapid, simple, and automated extraction system. I'm Laura Bush, the Editorial Director of LCGC, and I'll be your moderator for today's event. We're pleased to bring you this webcast presented by LCGC and sponsored by CEM. CEM is a science-based technology company dedicated to bringing new, innovative systems to the laboratory marketplace. Their goal is to simplify science by manufacturing automated systems for classic techniques that provide improved speed, reproducibility, and simplicity. We have a few housekeeping announcements before we get started. First, the webcast is designed to be interactive, so we encourage you to ask questions. You can submit questions at any time by typing them in the Q&A box, which you can find on the right-hand side of your screen. You can enlarge the slide window by clicking on the small square icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the webcast. And if you have any technical problems viewing or hearing the presentation today, please click on the question mark Help widget in the dock at the bottom of your window. I would now like to introduce today's speaker. We are very pleased to be joined today by Alicia Douglas-Stell. Dr. Stell has worked with CEM for the past 12 years, having joined the company after completing her PhD in analytical chemistry. Her extensive background in chromatographic analysis and her mechanical prowess have been instrumental in the development of the EDGE solvent extraction system and its applications. She has been leading the EDGE product since its inception and has traveled the world to identify new markets and develop applications for this innovative technology. Dr. Stell, thank you for joining us today. Please go ahead and get us started.
Thank you, Laura, for that kind introduction, and thank you for those who are listening in on the audience today to this talk. Before I get started, I want to make a quick note that I currently have a cold, so hopefully that will not cause any disruptions, but if it does, I apologize in advance. So as noted, the title of this talk is The Extraction of PFAS from Mixed Matrices Using a Rapid, Simple, and Automated Extraction System. So with that, let's get into it. What is PFAS? Well, PFAS are per- and polyfluoroalkyl substances. One of the structures of one of them here, this is PFAS, one of the key ones of interest. It is perfluorooctane sulfonic acid. And so this is, most of them have different carbon-linked chains, but they're fluorinated compounds. I'm not going to get too much into the chemistry in this particular talk, but just wanted to put a representation of the type of substances that we are talking about. But the reason we're talking about this, and I am sure that anybody who goes out there and Googles PFAS can see that it is a hot topic in the news today. It is certainly an emerging topic and will continue to grow as we realize the concerns associated with these substances. They are man-made chemicals, and so we brought this kind of upon ourselves. They have been used since the 1940s, so they've been used for a long time. And they're extremely persistent, and they accumulate in our environment. So this is really where the concern is. We're in the month of February here, and so we just got past Valentine's Day, and they say that diamonds are forever, but so are PFAS. They stick around, and when they stick around, they're also accumulating. Pretty much any one of us, we probably have PFAS in us as it's accumulating in our environment and in our systems themselves. Furthermore, remediation is difficult, so it's hard to clean up these substances. And they have been linked to adverse health effects. I really think that we're going to see more and more adverse health effects linked to PFAS. So this is a big problem. It's something we need to be looking at, and as I said, it's kind of emerging. We're starting to get methods in place as we learn more and more about this. So beyond the fact that the chemicals themselves are scary, They are everywhere. So pictured here is just kind of some of the places that we can find PFAS, but essentially it really is everywhere. The topic of PFAS has primarily been about drinking water to date. That's where our methods do exist, and that's kind of the logical place to start is the drinking water. But if it's in our water sources, it's getting into our soils, it's being consumed into our produce, and that's eaten by our animals, it's getting into our food stuff. And then furthermore, beyond that, it's in our cookware, the packaging that we're cooking our food in, the pizza boxes that we get pizza in, stain repellents, other consumer products. They truly are everywhere. So this is a really big concern because you can't really avoid them. I am giving this talk from North Carolina, and just in our backyard, the Cape Fear River Basin is one of the big concerns right now. So you really can't escape it, and it's something we need to take very seriously. So with that, let's talk a little bit about where regulation currently is at. In the United States, we do not have any maximum contaminant levels for most of the PFAS. There is a health advisory out there for PFOA and PFAS at 70 PPT, but that's even starting to decrease. So these are detected at very, very low limits. There are two EPA methods. We have EPA 533 and EPA 537.1. Both of those methods are for drinking water, and they both are similar processes in that you have your drinking water sample, you run it through SPE cleanup, and then you analyze it on MS. But drinking water is really where those methods lie. And what you'll note in this talk is I'm going to focus on samples outside the drinking water sector to talk about some of those solid substances. I'm going to talk about soil and then get into food a little bit. And as we continue this PFAS work, we're going to see more and more sample matrices becoming of interest. But really at this stage, we have to adapt all the methods kind of off of the EPA methods that we currently do have. The United States does have a PFAS action plan, so we're working cross-agency, being very diligent, so we are taking this very seriously. There's a lot of current work being done. If we go outside the United States, in Europe, Denmark has become the first country to ban PFAS, and overall the EU is working together to come up with regulation for PFAS. And I make that point, we really do, across the board, need to work together because as this is an emerging topic and is something that is affecting us on a worldwide basis, the best case scenario would be to harmonize methods so that we're all doing this in the same manner. Australia has been in the news a lot regarding PFAS, and they are working on a national phase out of PFAS. So really my point I want to make here is this is a global issue. It is something that as far as world people across the globe need to take seriously, and we need to come up with more and more methods and regulation for PFAS as we move forward. So as I mentioned, I'm going to talk more about solid samples, and particularly going to focus on soil to start with. So a typical extraction of PFAS for a soil sample would be what is pictured here. So essentially you would weigh about 1 gram of your soil into a centrifuge tube. You would then add about 8 mils of methanol. That would then contain your surrogates at that point. You would shake for about 30 minutes, sonicate for 30 minutes, and then centrifuge for an additional 5 minutes. Then you typically do an SPE cleanup. Typically it's some sort of graphite carbon black with an additional 2 mils, brings that final volume up to 10 milliliters. And then and you would add internal standards at this point as well. And then you would bring it over and run the analysis. So what you see is this is a very manual process. There's a number of different steps involved, and it takes over an hour to get through all of these steps. So what I want to talk about as an alternative method is using the edge extraction system. So the edge process is depicted here. In this case, you would assemble your Q cup that holds your sample. You would then weigh your sample, so that 1 gram, into the Q cup. You would load that into the edge and run your method. The method lasts for just under 10 minutes. At that point, you have your extract. It's ready to go. You're going to bring it to your known volume and then analyze it. So if we look at the two processes together, what we see is the edge cuts out a lot of those manual steps. It gives us automation. It's going to automate the actual extraction process, and in doing that, you gain efficiency, right? You're removing the human aspect out of this, so you get efficient, and then with efficiency, you get traceability, reporting options. There's all these other things you gain that are great for automation. I'm a really visual person, and so you'll notice a lot of pictures throughout this talk because I think they really kind of bring a message to life. And so with that, I want to watch a video of how the edge runs because you're kind of still probably like, well, what is that edge? So in this video here, you'll see Brittany is going to come and grab a Q-disc that enables our filtration, and then she's going to assemble the Q-cup. The Q-cup is made out of aluminum, so you can put it directly on an analytical balance. It's really light and weigh your sample in. You'll notice here that the racks that hold the samples are easily exchangeable, so you can be preparing samples while others are running. The system is going to run 12 samples in series. With just a few clicks, our methods are loaded. The automation is going to come down. It's going to pick up our Q-cup, and it is going to load it into our chamber. Once the sample is in the chamber, the actuator is going to come down and create a sealed environment. Once you have that sealed environment, we're going to add solvent by both the bottom and the top. This is going to fully wet our sample. Once our solvent is added, we are then going to start pressurizing and heating. As we pressurize, this creates a pressure differential, so that solvent on the outside is going to disperse up through the Q-cup, Q-disc into the sample, creating a dispersive effect which aids in the extraction process. Once we reach temperature and or hold time, it's going to drain through the Q-disc, through the cooling coil, so you're going to collect at room temperature, and then into your collection. We then add the option of a rinse where you can take clean solvent, run it through, and collect that as well. So you see that collecting right here. At this stage, your extraction is complete. You can be taking that and running analysis. However, we are running in series here. So we need to be cognitive of carryover, specifically for the PFAS conversation that we're having here today. So we need to make sure that we are completely clearing the system of any contamination. On the edge, you can run multiple washes with multiple solvents. You can add heat, hold times. You really have a lot of flexibility to make sure no carryover is going to be there. And you see the system now going over to our waste port and washing that entire fluidic pathway that saw a sample. So with that, the edge is complete. That entire process, you saw it running real time, so it's very fast. And then another really good feel-good thing about the edge is that your extracted sample, typically that's just waste. However, if you look at that, it is bone dry, and it was just in solvent. That dry sample and that clear extract gives you that feel-good moment that you got a great extraction. So hopefully that gave you a nice introduction to what the edge does and how it functions. Now that's our generic video. I'd be giving that video for any application that I'm talking about. So let's talk a little bit more in detail of what other things we took in consideration for the particular application of PFAS. So again, I want to note automation. That's really where it's at with the edge. We're automating what is typically a manual process. If you remember back to that flow chart for the standard method, they typically do an SB cleanup. So you can do that in cell on the edge. So in the case of carbon graphite black, you could just add some of that to your Q-cup and then your sample. So you can do that cleanup step during that automation process. And then simple, I think that's a little bit overlooked sometimes, right? But I think in the modern world, simple is so key. We are busy people, and we need to have simple processes because there's a lot going on in our world. And I hope what you see throughout this is that the EDGE is a very simple solution to a very complicated problem here. And then that next bullet point, multi-matrix, multi-residue method, I kind of stole that from some of my other presentations. I give a lot of talks on pesticides where that is indeed true. But as I was putting this presentation together, the parallels between some of the pesticide stuff was very clear, and even maybe more so, right? With pesticides, we have multi-matrix because we have a lot of different food stuff. But with PFAS, it's beyond that, right? We're talking now water and air and soil and consumer products and food stuff. I mean, it is really just everything. Even biological samples get into toxicology. So multi-matrix, I mean, it's kind of, sky's the limit on the different things that we could be looking at here. And then multi-residue. There are over 1,000 pesticides as well as PFAS. We continue to identify more and more PFAS compounds. So truly, when you have a method that can be applicable to a lot of different matrices for a lot of different residues, that is a big advantage. And that is true for the EDGE for this PFAS problem that we have. Now that next bullet point, PFAS-free, I'm going to dig in a little bit deeper here because this is so crucial for this particular application. So I have been working for an instrument company now for 13 years and worked with a lot of products, and almost every single one of them has Teflon on it, right? As instrument manufacturers, we love Teflon. It is robust and it holds up. It's inert. You can do high temperatures. It's all these great things that you want for instrumentation. However, we cannot have Teflon present when we're talking about PFAS because there's some PFAS components that could cause contamination there. So we need to eliminate any Teflon components on the system. So what we've done here is we've used PEEK and polypropylene tubing. We're using PEEK for our stationary tubing and polypropylene for our movable tubing, so anything that's doing the automation. Beyond that, we have added a side enclosure. The previous picture of the EDGE had that side enclosure closed. In this picture, you see it open. We just want to make sure that we have a completely clean environment, so when the system's running, you can have that enclosure closed and making sure no dust or anything is getting into the system. Beyond that, if you saw in the video, we were collecting in glass vials. However, we can also collect in centrifuge tubes, and we're going to do that for this PFAS application. We also have a nitrogen option. So the standard EDGE does not need any gas sources. It simply runs with air. However, for the PFAS application, you may want to be running in an inert environment such as nitrogen, and that is an option that you can do that also just takes that extra step to making sure everything is clean and PFAS-free. So we've kind of discussed about the components of the EDGE and make sure those aren't introducing PFAS, but we also need to look at our consumables. And there's a fair number of consumables on the EDGE, right? You've got your Q-disc and your Q-cup and so forth. So we took that very seriously and did soak test and looked at data to make sure that nothing that our sample came in contact with had any PFAS contamination. So we tested our Q-disc, we tested the packaging of our Q-disc, we tested our Q-cup, the centrifuge tube that we're collecting in, the extraction solvent. You're probably like, what is Q-matrix hydra? I will get into that a little bit later on, but we did use it in one of our sample preps, so we needed to test it. So we tested our Q-matrix hydra and the container that the Q-matrix hydra comes in, the pipette tips that we used for spiking, that tubing, both the polyethylene and the PEEK that we used, and then we also tested an edge blank. So anybody in this industry is going to take a lot of care to make sure that we are not introducing any PFAS into the system during the extraction. So I want to take just one step further here, because we talked about the instrument needs to be PFAS-free. The consumables that touch the sample need to be PFAS-free. But it's the entire process, okay, from the sampling of the sample to homogenizing to preparing the sample, that entire process through analysis needs to be PFAS-free. So some of the pictures here are just some of the things we used during our sample preparation to make sure that we were not introducing PFAS into the situation. And I'll specifically go over our steps when I talk about the different samples. But just quickly, kind of, you see that mixer there. We have to think about not every homogenizer is going to be okay in this case. You have to make sure you're not introducing PFAS into the situation. So with that, let's talk about the samples that I'm going to talk about here today. So we're going to start with soil. We're going to, that's kind of think that next wave of PFAS is going to be on those environmental samples. So we started with water, and then we're probably going to see a lot of focus on soil and more of those types of samples. But I also think it's going to branch into food. So we're going to talk about a produce sample. Specifically, we'll talk about cucumber, and then we'll go over a few of some packaged food samples as well. So with that, let's talk about how we would prep these different samples. On the edge, we're going to run the same method. However, we do need to be aware of how we prepare our samples with the different foodstuffs and so forth, the different types of samples that we're looking into. So what I'm going to do is talk through the slide from the bottom up. So if we start there on the bottom, we have to have our Q-disc. So the Q-disc that we are going to recommend for this application is our G1. That is a glass fiber Q-disc. It filters down to 0.3 microns, so you can go direct to your LC analysis. Now, if anybody is familiar with just glass fiber as a material, it's not very strong, and we're running under a pressurized environment. So what we've done now is created this sandwich of that glass fiber filter with our C9 filters, which are our cellulose filters. And so that just creates a really robust Q-disc combination that you can apply to any sample type. So same Q-disc we're going to run for soil, cucumber, and our packaged food. Then we have to, in some cases, think about adding sorbent to remove any interferences that we might have. For the soil, we're not going to add anything at all. Okay, so the soil, we're just going to go directly into the Q-cup. However, for that cucumber, it is a sample that contains a lot of water content, and that is where we're going to introduce our Q-Matrix Hydra. Now, Q-Matrix Hydra is a product that you can purchase directly from CEM. It is a polymer superabsorbent, and it does an amazing job at absorbing water. So what we're going to do is put 2.5 grams of that Q-Matrix Hydra at the bottom of the Q-cup and then our cucumber sample. And that Q-Matrix Hydra is going to absorb the water, so we don't have water in our extract before we go to analysis. For our packaged food samples, those contain some lipid interferences, so we're going to add 0.5 grams of C18 to remove those lipid interferences for those particular samples. So soil, nothing. Cucumber, we use some Q-Matrix Hydra, and for the packaged food, we're using a little bit of C18. Then across the board, we're going to weigh in 5 grams of sample, so 5 grams of soil, cucumber, and packaged food. And then we're going to spike. In this case, we used Absolute Standards PFOA DOD. It contained the 24 DOD compounds that they are looking for. Now, I do want to make a note here that for our study, we used Absolute Standards. However, I recognize that Wellington Laboratories is a very popular place to get PFAS standards, and I think they have a very nice selection as well as some CRMs as well. So if you just have that question of what other PFAS standards are out there, I did want to make a note that Wellington Laboratories is a really good place to go as well. So that's how you prepare your sample. So the differences of how we treat these samples occurs in the prep of that Q-cup. Then we're going to move on and run that same the same edge method for all of these samples. So I'm just going to talk about the edge method, and we use the same method for any of the sample types I'm talking about here today. I want to note that these screenshots for the method were taken directly from our software. So I hope you see just kind of that good user interface that we have, really simple, really amenable to making quick changes, and good for an R&D environment. I'm going to talk about 3 different levels: the settings, the cycles, and then the wash. On the settings shown here, pretty straightforward. We're going to name our project. We're going to pick our Q-disc. And then for collection, we have combine there. All that means is that we're going to be running a 2-cycle method, and we're going to collect both of those 2 cycles in one centrifuge tube. So our final sample is together in one collection. If we look at the actual cycle that we ran for this, please note that you probably can't read the solvent. So that is 80-20 methanol water with 0.3% ammonium hydroxide. And we used HPLC grade solvents for this study. So we did do a 2-cycle method. And if you remember back in the video, I talked about a bottom add and a rinse. But we're keeping this really basic and simple, and so we're actually going to just add for the top in these cases. So we're doing a 10 mil top add. We're going to heat to 65 degrees C. We're going to hold for 3 minutes for the first cycle and 4 minutes for the second cycle. So if you note that, that's got a total hold time of 7 minutes there, and then a little bit extra time for automation. In less than 10 minutes, your entire process is complete. I do want to cover the wash cycles, again, because carryover is something that we really need to be cognizant of, specifically for the PFAS conversation. So in this case, we did 2 wash cycles. We did 10 mils of methanol, followed by 10 mils of the extraction solvent, and then we held that for just a few seconds at 50 degrees C. And we've, obviously, with everything, we are collecting our blanks and running after and confirming that indeed no carryover is taking place. So this next slide, I really like to put out there because, again, I want to cover the details. Typically, if you, I watch a lot of webinars, and a lot of them deal with the analysis, which is really great work and things that we need. But often the sample preparation slide is either just one slide or maybe just not even mentioned at all. However, the sample preparation, these nitty-gritty details that we're getting into here in this presentation are important. In the world of extraction, if you don't do the sample prep properly, you don't get good analysis. So we need to be cognizant of how we're preparing our sample. So I don't want to just gloss over the details. I want you to be able to go back and reproduce it and be able to understand each step we took along the road. So for quantitation, you really do need to have a final volume. So we're going to dilute to a known volume to just be sure that we know that volume. And then also for this particular application, we neutralize with 20 microliters of formic acid. So at this stage, we are ready to then now do the analysis. And I will note that this was where we passed off the samples and outsourced the data. So everything up to that last slide we did in our laboratory, and then we worked with PACE Analytical, formerly Shealy Environmental Sciences, located in Casey, South Carolina. And I have to give a huge shout out to PACE Analytical because they have been so helpful in this project. They had really good turnaround times for us. They were kind enough to share their logo and their HPLC MS method here. They shared their SOPs, so we understood how they would typically prep their samples. And so that was all very helpful. So, thank you to PACE Analytical in this. So what they ran then the analysis on is a SciEx 4500 with an Agilent pump system. And the same considerations that we had to take for the edge as far as removing the Teflon components and so forth, the analytical companies need to take into consideration as well. So they're going to, in this case, they use stainless steel lines going into the mass spec and PEEK solvent lines and polyethylene tubing anywhere else. So you see a lot of parallels there of the same things we had to do on the edge. Also, there was a sample chiller at 4 degrees C for the auto sampler. They used a Phenomenex column with the specifications listed there, and then they had a guard filter and a delay column present. The reality here is PFAS is there. So you need these the guard filter, the delay column to really filter out any contamination so that we're getting good analytical data. Did a 10 microliter injection volume. The mobile phase was 20 millimolar ammonium acetate in water and methanol, a flow rate of 1,200 microliters per minute, and a pretty standard gradient. If you note, this gradient is just over 8 minutes long. So the extraction time was less than 10 minutes, and the analysis time was less than 10 minutes. So total process, you've got data in hand in under 20 minutes. That's really great for an R&D environment. I like to make note of how rapid this process really can be. So this picture here, and again, you're going to see a lot of pictures as I talk through my samples. And I usually do this in all my presentations, and sometimes I get a really pretty color story, and other times it's kind of okay. But these are the actual extracts we ran: soil, cucumber, a snack cake, and a turnover, and we'll get into the details of all of those. Please note that for visual purposes, I transferred these extracts into the glass vials because they look pretty there. We did, for any analysis, we used centrifuge tubes. But for pictorial purposes, extracts in the glass vials just give a better picture. And you can more clearly see the clear extracts and everything from there. So with that, let's talk about the soil sample first. So again, here's a picture of the soil pre and post extraction and the actual extract that we had. Not too much going on here. Again, like I said, these samples aren't the most visually appealing as far as the changes that occur. But again, I like to keep myself honest and show everything. You see a little bit of clumping of the soil because we're draining through that, but it's perfectly dry, and we've got a clear extract ready to go for analysis. I do want to note that for our soil sample, we used clean sandy loam from Sigma Aldrich, and we did note a few PFAS in the background of the soil itself. So we made a consideration of that for the data that I'm going to present here. So we wanted to do a pretty comprehensive study. So we're going to talk about a low spike, a mid spike, and a high spike. And we did 3 replicates across the board. And again, we spiked with that 24 compound standard. So I want you to be able to see my numbers. I'm splitting everything up into 12 and 12. So we'll have 2 slides for each of these to cover all 24 compounds. For the low spike, we spiked at 0.1 ppb. The limit of detection for this was 0.025 ppb, so just know that we're within the range of what we can detect here. And we got overall, PACE analytical requires an acceptable recovery range of 50 to 150%. So we wanted to make sure within that, but overall you see that we get good recoveries across the board and good RSD values for the 12 PFAS that you are looking at here. If we move on to the additional 12, we see the same story. Okay, so across the board for the 24, we got good recoveries and good RSD values for the low spike, which is the most challenging, really. So we're very happy with this data. I do want to bring attention to a few specific PFAS compounds. So PFOS and PFOA, those are the 2 that we have limits for right now, and of 2 of the more big concern ones. So I just wanted to, show that we've got good recoveries for those specific compounds. But also the PFBA, I just want to bring attention to that because that is just a pesky one. It is the one that's difficult to get rid of. So it's just as you work through this data to know, you really have to pay a lot of attention to that particular one because it tends to show up everywhere. So I just wanted to bring attention to that. If we move on to our mid-spike data, now this was spiked at 10 ppb. If anything, you see an increase in recovery and tighter RSD values across the board. And pretty much we would kind of expect that as we increase our spike. I do want to note that we are spiking here, and spiking we would expect to get good recovery values. If we move on to the next 12, we see the same story occurring, and we get good recoveries across the board and good RSD values. The next step in this study would be to run a CRM. So we understand that. We kind of, following this process of doing these spike studies, and then we'd run a CRM to really bring home the fact that this method is working well. So that would be the next step. If we move on to the high spike data, now this was now spiked at 20 ppb, you see the same trend of even higher recoveries and tighter RSD values for that high spike data. I do want to make a note that as you are increasing your spike value and you're getting hotter samples with these components, you need to be more and more aware of carryover. So I really encourage people to make sure that they're looking at their blank runs and verifying that the wash parameters are indeed correct, such that no carryover is occurring. So that is just something that as you get to that high spike to be more and more aware of. If we look at the final 12 components here, we see across the board, again, good recoveries and good RSD values. So this is going to conclude my talk on the soil, but I hope you see that we got a really strong set of data here showing that we can take that one edge method, apply it to the soil data, get an automated method that gives us really good recoveries for this PFAS compound. So let's talk a little bit now about a produce sample, and particularly we're going to talk about cucumber. Now I want to note that moving forward, we're not going to do any more spiking. We're just going to run the sample and show if any PFAS are present. This is all really preliminary work. There's more work to be done here. I don't know if there's really any methods out there to refer to with like a wet food sample at this stage. So this is really kind of at the beginning stages of the study and moving on to these more challenging sample matrices. So this is definitely preliminary work, and we have more work to do with spiking these compounds and so forth. But anyways, with the cucumber sample, we cut it up with a methanol cleaned knife, and then we homogenized it in that stainless steel mixer. And then if we look at the actual, more marketing stylized photos here, what you'll see is that, again, kind of same story, not too much transformation occurring here. That white substance for the post-extract is that Q matrix hydra that was absorbing the water, and then we get a nice clear extract ready to go for analysis. And then if we look at the data, we picked up some PFAS. And I don't know how surprising this is. I guess we would hope that there would not be too much PFAS going on in our produce itself, but we did pick up a few. I do want to note that I'm not talking about quantification at anything here, okay? I'm not talking about these were over any sort of limits. All that these were above the detection limit, so we saw that they were present, okay? And we certainly did run blanks beforehand and blanks after to prove that indeed this is coming from the sample. I do want to note that PFOA, one of those ones of concern, is one of the ones that we detected in this particular sample. So now I want to move on to a snack cake sample. So the pictures here are real-world pictures. These were just snapped, you can kind of tell, in lab as we were prepping the samples, keeping us honest of just the process and what was going on. So how we prepared the snack cake is we removed the icing and then chopped up the cake. Now, why did we look at just the cake? Well, we're looking really, what we wanted to look at is the part of the food that was touching the packaging, because we're thinking that primarily the PFAS contamination could possibly be coming from the packaging itself, and so we want to focus on the food that was in contact with that packaging. We dried the chopped cake for 1.4 hours in the oven at 100 degrees C, and then we ground it with a pesto mortar, which led to that final sample you see there, and then the extract that you see. If we look at the more stylized photo, you see that same process of the fact that not really any transformation. The white that you see going on here now in the post-extract is that little bit of C18 that we put in there to remove the lipid compound, and then we get that clear extract ready to go for analysis. And then, not surprisingly, we saw more PFAS in the snack cake than we did in the cucumber. And you know, again, I'm kind of happy. If we had more in the cucumber, I'd probably be even more scared. But that snack cake, you see it pictured there, that's what we ran. And then I have that PFOA highlighted because that was part of the ones that we did detect in this particular sample. Now let's move on to the microwavable turnover sample. You know, from the beginning, you're probably like, turnover? What is she talking about? Maybe now you have a little bit of a picture of what I'm talking about. You know, it's those turnovers that you put in that sleeve that you then drop in the microwave and heat up, and if I'm reading the packaging, enjoy. So again, the way we prepped this is we prepared the microwave turnover as instructed. So we heated it up, we did it as in the microwave, and then we removed the outer bread. Again, we were looking for the sample that was in contact with the packaging, and then we dried that outer bread in the oven for 1.5 hours at 100 degrees C, and we ground that with a mortar and pestle, and then you see the actual sample we had there, and then the extract that we got for analysis. And the same story here with these pictures. You see that kind of, if anything, the sample starts to clump up a little bit, but it's still perfectly dry. That has that white powder of the C18 present that we added to remove the lipids, and then a clear extract that we took for analysis. So then if we look at the data here, maybe not surprisingly, even more PFAS. So a lot of hot ones for this particular sample. So I don't know how much, you know, as I prepared for this talk, you know, I stopped using my Teflon-coated pans. I've really thought about some of the food stuff. You know, I guess I was just kind of naive to how many different components are out there that really are exposing us to these compounds. In this case, we pick up both PFAS and PFOA, so those two ones that we're paying particular attention to. So overall, again, I want to note, this is a beginning study. We're working with some challenging substances here, right? You know, once we get into these food stuff with all these different components, extraction becomes harder. And so what I hope you see is that we were able to extract these compounds at the beginning level, but clearly we need to show moving forward spike values so we get good recoveries and RSD values. But I feel that, you know, the edge is going to be very applicable to all of these samples and beyond. So with that, I want to kind of conclude. So I hope you've seen throughout my talk today that EDGE instrumentation is PFAS-free, and that there's no contamination from the sample preparation or the consumables. And then for that soil sample, we got good recoveries and RSD values for the low, mid, and high spike. That we found PFAS in cucumber, snack cake, and turnover. And that overall, the EDGE is a rapid, simple, and efficient technology for the extraction of PFAS from mixed matrices. And I want to just expand upon that just a little bit right now, right? Because kind of to go back to the beginning of the talk and saying how the current talk primarily is water. Right, that's where our EPA methods are for drinking water, and it's where most of the work has been done to date is on water samples. And I don't want to completely exclude water as a possibility to run on the EDGE. Now, the EPA methods are for 250 milliliters of water. Now, 250 milliliters is outside the scope of what we could run on the EDGE. However, if we considered maybe concentrating that sample size down and running some sort of supported liquid extraction and or running a smaller sample size, we could indeed be able to run those liquid samples, those water samples, on the edge. And then as we open up that realm of liquid samples, we could do dairy. You know, milk is a very hot topic right now. So I hope that you see for mixed matrices, it's not limited to what I've discussed here. We can do water and soil and even get into air monitoring, the food stuff that we're talking about, the packaging. You know, that was our next step too, is to actually look at the packaging itself and what components are all of that. All of those matrices you can run on the edge. So with that, if any of you guys have ever heard any of my webinars before, you know that I like repetition. I have a 5-year-old daughter, and I think as I went into parenthood, it hit me how much repetition truly does help us in the learning process. You know, I am amazed at how many times, you know, my daughter can watch the same episode on something. However, she's, you know, really getting a lot of information, and she's learning during that process. So I like to repeat. So I'm going to kind of bring this full circle. It was the title of the talk. I covered it in the conclusion side, and now I'm going to say it again. Rapid, simple, and efficient extraction of PFAS from mixed matrices. If you take anything away from it, just the simple title is what I want you to remember, because that's what the truth is. The Edge offers a rapid, simple, and efficient extraction for PFAS from a variety of different matrices. Now, I would be remiss if I didn't talk about how good CEM's sales and service teams are. We truly are where you are. We have 60 associates in the United States and Canada alone, and then we have 24-hour telephone support. And again, I've been working with CEM for a long time, and one of the main things I continue to hear from our customers is how great our support really is. We are here for you. And I'm just talking about our sales and our service teams right now, but beyond that, my team is here for you. So my team is pictured here, and we are always accessible at molecular.support@cem.com, and we are going to assist you in any questions that you might have. And we look forward to conversing with you. I want to thank our CEO and owner, Michael J. Collins. He is not pictured here, but in the picture you do have myself, Brittany Leffler, Candace Calder, Candace Cashman, Benedict Liu, and Maria Swayze. And I cannot say enough about my group. They are amazing. They truly have, you know, they do everything I need. I couldn't do what I do without them. So a big thank you to my group. But here at CEM, we pride ourselves that we have a 1-to-1 ratio, really, of scientists to engineers. And so while I do not have the engineers pictured, they are crucial to this study, and we would not be where we are without them, and we are communicating with them on a daily basis and working with them. So a huge shout out to our engineers as well. So with that, I am going to push it back to Laura for any questions, and I thank you for listening to me here today.
Thank you, Dr. Stell. We've got a lot of questions coming in, so let's jump right into them. So here's the first one. Can this system be used for other analytes besides PFAS?
Yes, it definitely can. Now, well, okay, let me take a step back. The Edge can. But as you noted, that we had to take considerations for the PFAS system, particularly that has different tubing. So if you purchase a unit that is specific for PFAS, that is a unit that is only for PFAS. So I actually have to apologize, because the answer really is no, because that PFAS unit is definitely specific towards that particular application. However, if you order an Edge that then has our standard tubing and so forth, that is applicable to a wide variety of applications, from environmental to food and pesticides to phthalates and plastics and so forth. But yes, the actual PFAS Edge that has all the considerations with the different tubing and so forth is specific for PFAS extraction.
Excellent. When you say in-cell cleanup, how does that work?
Yeah, and I think that's pretty crucial to this study here because the EPA methods, or at least for the water, are calling for that cleanup, right? And so potentially it's going to be written into the method, and so you're going to have to do some sort of cleanup. So we certainly need to make sure that we are addressing that on the edge. And so what you do is just, weigh in whatever sorbent you need for cleanup into the Q-cup. So as you prepare your Q-cup, you put that Q-disc in, you assemble the Q-cup, you put it on your balance, and then you're going to weigh in the sorbents that you need to remove those interferences to your cleanup. So in this case, if you needed some graphite carbon black in there, you would weigh that into the Q-cup at that time, then you would add your sample, and then you would drop that in the edge. So that cleanup step is happening during the extraction process.
Is the whole open area in the edge covered with nitrogen?
So no. So with the nitrogen option, so on the edge we have an internal pump. And so any single time the pump is used, so that's when it pressurizes the initial cell, and then we use that for purging, it is pulling air. So the way the nitrogen works is that you plumb basically nitrogen to the bottom of that pump, and so instead of pulling air, it pulls nitrogen. So it replaces nitrogen, puts nitrogen in for those steps that we would use air for. So for pressurizing the chamber and for purging your sample at the end. That environment, that tray area where your samples are sitting, that is not coated in nitrogen. So no, that would not nitrogen. It would not be a nitrogen environment at that stage. Once it is in the chamber, through the time the extract is collected, that's where the nitrogen environment would be.
You mentioned multiple cycle methods. How many cycles can you extract with?
Okay, that's a good question. Actually, really, you're not limited. So you have 12 positions on the edge rack, and you can run 12 cycles if that's what you wanted to do. So you have that versatility of really doing a lot of good R&D work, particularly in, say, the polymer industry, and that might be applicable to PFAS because we want to maybe look at the PFAS present in those compounds. They're going to want to do like an exhaustive study where they do as many extractions possible with cycles to really see at what point we exhaustively have extracted everything. So the edge really pairs itself well to that because you can run up to 12 cycles and collect in the entire rack if that's what you wanted to do for one sample.
Why was carbon black not used in the soil samples? Do you think that would have improved the data?
Yeah, and actually that's a good point. I kind of didn't really get into the details on that at all. I think, for the everything that we did here, it was just straight sample, no carbon black. And we wanted to go as simple as possible. And so I think we want to just kind of start at the ground with sample and then kind of work our way up. We certainly, that would be part of our next study is to add the graphite carbon black. But yeah, I think there is a possibility that it could even improve the recovery. So yes.
How much of a liquid sample can be run on the edge?
Yeah, it's a good question. So typically we'll support that liquid sample on the Q matrix Hydra, which we have ran to prove that there's no PFAS contamination on that. And usually you can run about a 1-to-1 ratio of liquid to the Q matrix Hydra, and we usually recommend no more than 10 grams. So that would limit you to 10 grams of Q matrix Hydra with 10 mils of a liquid supported on that. So I would put that limit at about 10 milliliters.
I have a related question here. I'm not sure if this was just answered, but I'll ask in case. Does the sample need to be completely dried?
So no. I mean, so maybe for best results, right? This is a preliminary study. And so that factor of how much a water content in the sample may be affecting the results is kind of unknown at this point. But what you'll note is that we did dry the package samples, so we did dry those in an oven to remove any water content there. However, we didn't dry the cucumber. And the cucumber obviously has a very high water content. So again, we have to move into those next stages of spiking and getting recoveries and really prove that we can do it. But right now, if I kind of jump over to pesticides, we can run wet samples no problem and get really good recoveries for pesticides. So I think we might be able to develop a method here where, yeah, we don't have to dry the samples. So you could run them wet.
So after extraction, do you inject from that liquid directly, or is there more sample prep or dilution? And where do you add the internal standards in this process?
Yeah, okay, that's a really good question. So yes, no, you direct and directly, right? So when you collect your extract on the edge, it is filtered, it is ready for analysis. We do, like I said, on that kind of post step slide, you may have lost a little bit of solvent during the process, so you're going to want to dilute to a known volume. But typically, you're just using the graduations on the centrifuge tube there, and maybe adding in just a few drops. If you didn't want to do that dilute step, you could, pour it into a graduated cylinder and see what your volume is. You just need to know exactly what your volume is for quantitative analysis. And then you would, in this case, we did neutralize with formic acid as well, and then we went direct to analysis. As far as the standards are concerned, we're adding surrogates at the very beginning. So when we spike and we got our surrogates there, but also we add an internal standard to make sure the analysis is good right before injection.
Is there any regulatory requirement for PFAS in food and water?
So there is the EPA methods, 533 and 537.1, that is for drinking water. So right now, those are the only EPA methods that we have. And as I said, there is a action call for limits for PFOA and PFAS. But that's really all we have at this point. So no, there's no methods beyond that. So as we talk about soil and food, this is still in the process of these methods are being developed. There's no official methods available at this stage.
This is a multi-part question, so bear with me. Did you do a concurrent analysis of the packaging of the snack cake? The implication is that the PFAS migrates from packaging. And how might the extraction change?
Yeah, that is a great question, and to be completely honest, I hope to have that data in this presentation. We just, again, this is a preliminary study, and that's what I had at this stage. That is very much our next step, is to run the packaging and to look at that. I did mention we use that exact same method for the soil, the cucumber, and the packaged food. But when we start getting into more packaging and polymer-like samples, if you kind of can imagine, if you're doing extraction of those, we need to be able to kind of transform them, right? Kind of get to that molten point where we're absorbing into and getting into the sample. And to be able to do that, we do need to add a little bit more time to the method. So I would say for the packaging, we would adapt our method just slightly and add a longer hold time, just because you need that time to really penetrate those types of samples to get a good extraction. But yes, certainly the next step is to look at that packaging, and I said we'd probably implement probably closer to a 10-minute hold time for that particular method.
How do you choose the best extraction temperature according to the selected solvent?
Yeah, so on the edge, you can run temperatures anywhere up to 200 degrees C. And also from the pesticide realm, sometimes they don't want to add any temperature at all. So I like to say that temperature is an option, not necessarily a requirement. So it really is a large spectrum, and choosing that temperature has, I'd say, more to do with the analytes you're trying to extract than the actual solvent that you're running. For pressure restraints, there may be some solvents that you're not going to want to take all the way to 200 degrees C, such as say you were using diethyl ether or something like that. You may want to limit that just because you're going to start building up a whole lot of pressure. But from actual extraction point, it comes down to more of the fact that you want to not degrade your analytes. So for pesticides that can tend to start to degrade with temperature, you're going to want to keep that temperature low. But say something like dioxins that are known to be, really, okay temperature thermal, then we're going to want to go pretty high. In general, more heat aids in an extraction. So if you can put more heat in there, that's usually beneficial to the extraction, but you need to be cognitive of what you're extracting and how that's going to affect that.
Great. I'm going to squeeze in one last question. If we extract the sample again after the first extraction, will we not see PFAS? In other words, no leftover PFAS in the sample?
Yeah. We didn't do that. I mean, we didn't do an exhaustive study here where we did like multiple cycles. So we were just collecting the 2 cycles, and then we ran a blank after we removed the sample. So that would be something we could add into the list of what we run, is to do that exhaustive extraction that I talked about to show that we no longer are getting any PFAS out of there. And that is a good rule of thumb when you're developing methods to do that. Like I said, this is preliminary data, so that's part of next stages as well.
Fantastic. Well, with that, we'll wrap up. Dr. Stell, thank you so much for your excellent talk today and for answering all those questions.
Thank you.
I also want to thank everyone in the audience for attending and participating in today's event. And I'd like to thank our sponsor, CEM, for making today's webcast possible. You'll receive an email alerting you when this webcast is available for replay. We invite you to forward that announcement to your colleagues who might have missed today's live event. We hope to see you all next time. Goodbye.